Hello, everyone. Thank you for joining and welcome to today's webinar, Introducing the ENVI Deep Learning module. My name is Megan Gallagher, and I will be moderating this webinar. I'm excited to be joined by Zach Norman, who will be introducing some of the major new features and functionality of this exciting addition to ENVI. Just a couple of housekeeping items before we get started. I've muted the phone lines for all attendees, so if you have any questions at any point during the webinar, feel free to enter them into the questions chat box. We'll try to answer as many as we can at the end of the presentation. We are recording this webinar, and we'll have it up on our website at www.harrisgeospatial.com in the next couple of days. We'll also email you a link to the recording, as well as the slide deck that you're welcome to share with your colleagues. And now I'll turn things over to Zach so we can get started.
Thanks, Megan, and thanks everyone for joining us today. Let's go ahead and jump right in. So before we get going, this is me. So maybe I look familiar if you've joined in one of the many other webinars I've led. There's my contact information, and then we also have the email address for Harris Geospatial overall. You can reach out to me with questions you have. I do ask that you respect my time since I do have a day job. So if I'm super busy, I might pass you along to somebody else if they've got the time. So with that out of the way, here's what we're going to be covering today. Altogether, this will probably take about 40 minutes. We're just going to do a very quick introduction and background on who we are as far as Harris Geospatial. Hopefully most of you are familiar with that, but if you're not, I'll just be real brief. Then we're going to spend about 10-15 minutes going through just a background on machine learning and deep learning and talking about some of the differences between the two and trying to set expectations as far as what you might need to do if you're new to deep learning, because it is a different workflow than traditional remote sensing, especially for going through and extracting features. Then we will dive into the deep learning module and talk about the inputs and requirements in order to use the tools. We'll also spend some time on the different parameters that you can use to go through and tweak the deep learning models that you'll be generating and improve their performance. Then lastly, and probably the most important part of what we'll be covering today, we're going to be walking through 6 or 7 different examples of all things that were extracted using the deep learning module. We'll talk a little bit about how much time and effort went into each one. And I think that's really the most important, because if deep learning is new to you, I think it's beneficial to see some different examples of how you could use these tools. And with that, we're going to jump right into our content. So if you're not familiar with us, we are part of Harris Geospatial Solutions. So we're a small part of Harris Corporation. We're about 200 people. And really our core products and technologies are about remote sensing and image processing, image science. So ENVI is our core product or technology. That's the little ENVI Analytics up there in the top right. And IDL is kind of the backbone to ENVI. And so, I spend a lot of my days programming with IDL, automating workflows and writing different algorithms. So we do many, many other things apart from just that. You can check out our website to learn more about us. Check out our website if you want to learn more. And let's go ahead and start with the content. So starting with machine learning and deep learning, let's take a step back and talk about what machine learning is. So hopefully the nice little animation looks well over GoToWebinar. We're talking about machine learning. It's not Terminator. This isn't Arnold Schwarzenegger and Skynet. This is not, we call it artificial intelligence, but it's not some super amazing smart machine. So this is really just algorithms that go through, and without you giving it specific instructions, that algorithm figures out how to solve a problem. And with that problem solving, I think it's nice to talk about machine learning at a high level as far as how it really works. There's a lot of different algorithms out there. Deep learning being separate than a lot of machine learning algorithms. Machine learning, maybe you're familiar with random forest, or maybe like multi-layer perceptrons, which are just basic neural networks, or softmax. And really, with machine learning and deep learning, it's really just algorithms that minimize the difference between the results of that algorithm what it predicts and what it should be predicting, which that's where you come in as the user. As you tell it what it needs to find, whether that's classifying pixels, going through saying, oh, this is supposed to be, a tree or water or something like that. And those machine learning algorithms just go through and try to minimize the difference between what they predict and what they should. So with deep learning, if you've used open source tools before, the metric that's usually being minimized is loss, which is a representation of how that neural network is actually learning the features it should. And just with that quick overview, let's jump into deep learning for a couple of slides. Deep learning is a subset of machine learning. It's really where you start to get into having neural networks, convolutional neural networks, that try to work like your eyes do, eyes in the human brain for extracting features. Kind of the image over on the right-hand side there, as it goes from the bottom with those little red arrows up, different layers of neural networks go through and identify different features. So like if you're extracting a car, one layer of your neural network might go through and find something like doors or tires or the windows. And then as it goes through, it starts to put together that whole picture of what makes up the car and give you your result for detections. And so with that, kind of a high level, this might be a slide that you have seen before. I really like it, mostly just for the chihuahua with the sombrero on, for object detection. So object detection is a very common use case, especially if you're here because you're using remote sensing and imagery. We're going through and we're detecting features in imagery. So driverless cars, another great example of object detection as well. And while machine learning and deep learning, there's many different applications and ways that you can use the technologies, especially if you're not familiar with it. I think it's really important that you understand limitations and set realistic expectations for performance. Now this screenshot here, this is from an article that was on the BBC. There's a link down there at the bottom. And in this article, they were talking about how, so for extracting the stop sign, if you put a couple pieces of tape on the stop sign, then deep learning no longer identifies that as a stop sign. So even though there's a lot of really cool things you can do with these tools and technologies, I think it's important to level set so you don't think you can go out there and take the world on with machine learning and deep learning. While they are great tools to have in your tool set for image processing, understanding that they're not going to solve all your problems and there will be cases that they fail. So with that, let's talk a little bit more about some of the differences between machine learning and deep learning. And I kind of have put this list together from, I've used machine learning algorithms a lot, and I've also used deep learning a lot. And so these are kind of the main differences, I think, which are important to understand, because that way, if you sit down, if you're used to machine learning and you want to get into deep learning, then you are knowing what to expect when you get started. The main thing here is that second point, where with deep learning, it can take hours or days to go through, train a neural network, and get answers. Now that depends a lot on how much data you have and your hardware, which we will talk about hardware once we get to the ENVI Deep Learning module. Machine learning, on the other hand, it can take minutes or seconds to go through and generate a classifier and get results for your input data. Couple of things to note about other differences. So deep learning is primarily using a GPU, so graphical processing unit, NVIDIA graphics cards. Machine learning can be CPU or GPU, depending on what you're doing. One of the primary differences I consider to be between deep learning and machine learning is when I think of deep learning, it's mostly spatial. When I think of extracting features from imagery with deep learning, we're looking at spatial context. We're not sitting there and doing spectral analysis, looking at pixel values or finding end members or other things in our data. If you're a remote sensing scientist, hopefully that's familiar to you. But when you get machine learning, you're typically just looking at a single pixel. And so deep learning, that big difference is you have a whole chip of data. You have that context. You can see all the features around, extracting something like buildings or roads, versus traditional machine learning just being spectral. So there's other differences beside these, but these are what I consider to be some of the most important ones. So with that, getting into the ENVI Deep Learning module. So a couple of quick notes. The deep learning module is built on TensorFlow and Keras behind the scenes. And so it's basically just a way that you can run TensorFlow and Keras without needing to be a programmer. Of course, if you know IDL and you're the ENVI Task API, you can also use that to automate this workflow. But within ENVI, it's really nice because you can sit down, you can create training data, generate your models, see how those models perform, and kind of complete the cycle again. So this little deep learning pie is kind of the workflow when you are wanting to use deep learning to extract features from imagery. It is absolutely iterative and depends a little bit on how much data you want, and if you're trying to make a production level model from deep learning, or if you just have a couple of scenes to go through and process. So if you guys have questions or want to know a little bit more, feel free to use the little questions chat box, and we'll discuss those when we get to the end. But with ENVI and the deep learning module, one of the important things, which I mentioned a few minutes ago, is you need an NVIDIA graphics card to be able to use these tools. So this is another important thing for setting expectations. Don't expect to be able to install ENVI and the deep learning module on a 5-year-old laptop and expect to have a good experience. Your graphics card might not even be supported. And in addition to that, hardware is really important as far as how much RAM is on your graphics card, and then even just having a solid state drive. So that RAM and solid state drive are great ways to improve performance and reduce the amount of time it takes to actually generate models. So solid state drive I really recommend anyways if you're doing remote sensing, just because the file I/O, reading and writing data, is such a long part of that process. So you will need a graphics card. So if you want to use the deep learning module, note that you need a graphics card to go with it. So now that we got that out of the way, let's talk about what actually is a part of the tool. So the deep learning module, there's a little new toolbox. So screenshot on the left there. One of the things I like about the toolbox, a little detail, is the icons are brains. So for deep learning. And then there's the little deep learning guide map, which is the first item that's listed in the toolbox. And that's shown on the right. And this deep learning guide map is really nice, mostly because if we click on the little tools icon in that deep learning guide map, there's train a deep learning model using the ENVI modeler. And then there's also randomizing parameters for you using the ENVI modeler. So if you're not familiar with the ENVI modeler, it's a part of ENVI. It's been around for a couple of years now. We're basically visually creating workflows. So you don't need to be a programmer to go through and automate a specific process. So the thing that's really nice about this is I can open up that deep learning guide map, click train a deep learning model, and after a few moments, the ENVI modeler will appear with this workflow. If I click the little run button that's in the top of the ENVI modeler, that'll actually create an interface for me. It'll pop open and it'll ask me for an input raster and an input region of interest. And so this is really nice because without doing any programming or needing to do anything, I can just open up that workflow in the modeler, hit run, and start training neural networks and classifying imagery. So that's where this is really nice, and it works really well with ENVI. So let's take a step back and talk about some of the inputs that you need to use the deep learning module. So as I just mentioned, if you run the default model in the ENVI modeler, it'll prompt you for an image and a region of interest. So images, it's important to just take a second to talk about this because ENVI has wide support for many file formats. And so for the data that you process with deep learning, you can have any number of bands. there's some considerations with hyperspectral data, which I'll try to remember to mention before we're done. Your data can be of any state. So if you're familiar with the remote sensing workflow and you're a remote sensing scientist, you can have your due diligence and go through and do radiometric calibration, atmospheric correction, all that pre-processing to make sure your data is consistent and accurate. Your data doesn't have to be geolocated, so you could just have any sort of picture. It doesn't have to be something that's on a map, or hyperspectral. You can use multispectral, RGB, panchromatic, just about anything. So one important note on the data. So if you have any number of bands, and it can be any data type, what ENVI actually does behind the scenes is it normalizes your data and scales it from 0 to 255. So that way you can provide any source of data, and it will be kind of normalized and scaled so that your models that you train are more consistent, and then your results will be more reliable. So there's also, apart from that, I like this slide here just to call out that there's a lot of different data sources that we support in ENVI. And all of those data sources that are supported in ENVI, you can then use with deep learning. So whether that's UAV collects, very high resolution, you have airborne, kind of mid resolution, or satellite, which is probably going to be lower resolution. A couple examples that I'm going to show at the end are using SAR data. So Megan Gallagher, our moderator today, is our resident SAR expert. And you can go through and process SAR data, generate derived products, such as intensity images, and you can use those with deep learning. For LiDAR, even though that's a point cloud, you can go through and you can generate raster products from the point clouds to go through and extract features. And there's a cool example of that, which I will talk about as well. But here it's really, you can be as creative as you want. You can generate products from point clouds. Maybe you want to get the height of all of the features in your scene, and then you can go through and stack that with your source imagery. So there's a lot of potential and possibilities for what you could do with this. Getting back to the inputs for the deep learning module. So the second thing you need is a region of interest. So there are a handful of ways that you can get regions of interest in ENVI. The one that we most commonly use in ENVI land is the ENVI ROI tool. So that's there's a little red polygon up in the top of ENVI's toolbar. So if you're familiar with ENVI, hopefully you know where that is. You can add points, polylines, or polygons through the ROI tool. There's also some other shapes in there as well. You could use the ENVI feature counting tool. So the ENVI feature counting tool, which is shown on the left, for going through and clicking on the center of different cars, for extracting cars, which will be one of the examples I'll talk about. That's another way that you can get locations of objects you want to extract. If you already have features digitized and in shape files, you can import those directly into ENVI and use those for deep learning. And then another feature, which maybe you haven't heard about, so you can also access OpenStreetMap data within ENVI. So you can download OpenStreetMap vectors over a scene, whether that's roads or parking lots or any one of the numerous features that's part of OpenStreetMaps, and you can use that for training without needing to do anything by hand. And so talking a little bit more about why the ENVI Deep Learning module can be helpful and beneficial, especially if you've already used open source tools. Maybe you're a programmer and you are very familiar with the workflow from Python. With the ENVI Deep Learning module, it's really nice because you don't have to be a programmer. I've said that a couple times, but I think it's important to reinforce that. There's some secret sauce behind the scenes in the deep learning module, which allows you to, number one, use a single image for going through and generating a model. So you can label and train just a single image to make a classifier. And so it's sped up so that you don't need much training data. And it's also set up so that you can use points, polylines, or polygons. So if you have used open source software, like I have, polygons are the easiest to use for training neural networks. Polylines can be done, they're a little bit harder, but points are really tricky. And so there's some features, some parameters, which we'll talk about, so that you can use points and polylines and reduce the number of clicks it takes to actually get training data, which is a very time-intensive part of this process. So talking about the parameters, so this is the little interface for going through and generating a neural network with TensorFlow and ENVI. So specifically, this is using a UNet style architecture behind the scenes. So the parameters that we can set for this are patch size, loss weight, and class weight. And then we also have two distance parameters, solid and blur distance. So let's take a look at each one just to give you an idea of what they are and how you can tweak them to adjust performance. So patch size. This is a really important one, especially if you're not familiar with deep learning lingo. Patch size basically indicates how large a specific tile of your image is when it's pulled out and fed into the neural network. So most often this would be something like 512 by 512. You could also have larger or smaller. So the patch size is really important because as your patch size goes up, the amount of RAM that your graphics card needs to have also goes up. And so if you don't have a good graphics card, say you only have 4 gigabytes of RAM, you're going to have to set your patch size to be smaller, which is going to take longer to go through and do training. So you can make these usually as big or as small as you want, provided you have enough RAM or hardware to actually go through and process all of those. So for this little example, that red square might indicate a chunk of your data that's actually read out and then fed to the neural network for training. Moving on to our next parameters, let's talk about weighting our data. So weighting our data is really important, and that's where the class weight and loss weight come in so that you can tune your performance. The reason that you usually have to mess around with class weight and loss weight are because we have unbalanced training data, which really just means that the features we want to extract in our scene are small compared to the total number of pixels or area. So one of the examples that I'm going to be talking about is iceberg detection. And icebergs are pretty small compared to our overall scene. So I can set the class weight to affect how much data with icebergs in it the neural network sees. And so that's, basically biasing the neural network to see a lot more of our feature of interest at the beginning, which helps it train faster. In addition to that, you can use the loss weight parameter, which basically tells the neural network how important our pixels are that represent the features we want to extract. So the loss weight, you'll usually turn up if there's confusing features in your scene. So like with the icebergs, there's some islands with snow on them. So the snow on those islands is similar to icebergs. And so we can turn up our loss weight to emphasize that our iceberg should be detected, and we don't want to focus on the false positives, which is the snow on islands. So in addition to that, there's two more parameters. The solid distance, which this one is pretty straightforward. It's basically just growing all of the labels or regions that you have selected by a certain number of pixels. So this example is growing this little diamond shape by 60 pixels. So it's a little bit more dramatic. The reason that you might want to use the solid distance is if you have points or polylines as your labels. So for example, if I want to go through and extract ships, if instead of needing to draw a polygon around the outside of my ships, I could draw just a polyline down the middle, which will mean I only have to click 2 times instead of maybe 4 or 6. And then I can set the solid distance. So I have a line down the middle of the ships, and then the solid distance we can use to grow that line to fill the entire shape. So that's really nice because then it takes less time to label. You probably label about twice as fast if you just have to do polylines instead of polygons. So the other parameter that we have is blur distance. So blur distance is exactly what the name sounds like. We're going through and we're kind of smoothing the data before it actually goes into the neural networks. And this is really nice if your shapes or features have inconsistent sizes. So going back to the icebergs example, if I have icebergs, they vary widely in how big or how small they are. So I could click at the center of icebergs. I could use the solid distance parameter to grow to kind of the minimum radius. And then if I have some icebergs that are much larger than some of my other ones, I could use blur distance to kind of add a little fuzziness, you could think of it, to the shapes. And so then it could learn to extract the larger features and the smaller ones all at once, just being able to use points as labeled data. So instead of needing to go through and generate polygons around the edges, that's one way to help also reduce labeling time. And so circling back again, just to reinforce a few things that I've been saying. So, there's a lot of great tools in ENVI that really make sense for using ENVI and deep learning together. A really big part of that is on your data pre-processing and calibration. One thing that's really important when you are using deep learning, especially if you have more than a couple of images to go through, process, and classify, is you want to make sure you have a very consistent data range. So going through with ENVI, doing your pre-processing and calibration, or just making a nice pretty picture with stretching, that will help make your training be more performant, and then your classifier, when you're applying that to new images, will also perform better. So you can create automated workflows for pre-processing your data. Then you can use that same automated workflow to pre-process your image before classifying it with the model that you created before. And then I mentioned this quickly, but data fusion is also really important. Adding in other layers of information for some of these, for some neural networks is a great way to help improve accuracy and really delineate your feature of interest from other things. So whether that's, 3D data, so you're looking at the height of different features, maybe you're deriving some piece of information from SAR as well, being able to take all that together, stack it, and send that into training, and being able to do all that just within ENVI is where it's really nice. And so with that, that's all I have for talking about machine learning, deep learning, and the module. Let's go ahead and show some different examples so that we can maybe get a better understanding of some of the features that we can go through and extract with deep learning. So the first example here is taking a look at detecting landslides. So this is a region where there's landslides and flooding. I believe it was from Cyclone Idai from a couple of weeks ago or a month ago. So we have our before image on the left. This is PlanetScope 3-meter data, 4 bands, so blue, green, red, near infrared. So before is on our left, after is on our right. For this one, what I did was where there was some flooding in the rivers, which you can see on the right-hand side, and where there was flooding and some landslides, I created polylines. So I spent about 2 minutes going through and tracing down some of the flooded areas with a polyline, and then I trained, and it took about 15 minutes, and then I'm able to go through and here's the feature that's actually extracted. So this is something you could potentially do with traditional remote sensing, just looking at change detection and other things like that. But there's other natural change in the scenes. There's clouds, it's kind of hazy, and sometimes that can be hard to filter out. And so that's where deep learning is nice, because it figures that out for you so that you don't have to. Moving on to the next little example, iceberg counting. So I referred to this one before, and this is a nice one to talk about as well, because we're doing things more the right way. So in the previous example, I'm labeling and training on the same image I'm classifying, versus this iceberg counting, we actually start to separate things out. So I have a separate data set for training, and a separate data set that I'm going and classifying and trying to count the icebergs. So other important concepts here as well. When we go through and we use deep learning, we get an image out. That image represents how likely it is that each pixel belongs to our feature of interest. So as we go through and classify our data, we just get an image, and that's not really the helpful information. So the actual workflow for this iceberg counting is classifying our scene, then we go through and we convert that to a classification image, export that to a shapefile, and get the centroids of each one of our shapes so that we can get a count. So actually extracting vector information and not just making an image. Moving on to the next example, this is where this one's really nice because it's using derived information from a point cloud to go through and extract roads. So here on the left, we have an RGB representation of the height of different features. It's the intensity values from the point cloud, so that's the LiDAR returns. And then we generate a shaded relief to add a little bit of texture to the scene as well. And so this is also a really nice example. So this was using Geiger mode LiDAR. And one of the things that's nice about Geiger mode is that it has foliage penetration. And when you're extracting roads, depending on where you're located, there can be a lot of trees over the roads. And so if you notice, looking at this image, there are no trees in this scene. You'll see some kind of dark shadows over roads. Those are actual shadows in the intensity from where trees were. We went through and removed all the vegetation. And so using LiDAR, we can see through obstructions that would be challenged to use with just imagery. And we can go through and generate a model and extract all of our features. So this is really nice just to show that sometimes you can think outside of the box to go through and solve problems to extract different things. Moving on to another example, ship detection. So nothing super exciting here. Just to show you, for this, I went through and I used polylines. So just as I described when I was talking about solid distance, I just click at the front and end of the ship, and then I use the solid distance parameter to grow those polylines to fill the shape. And then when I go through and generate a model, I can see all of my results for extracting the features. Another good example here, just to show kind of the art of the possible, is using SAR. So this was an image that Megan generated for me. It was an intensity map from the flooding in Nebraska from a couple weeks ago, a month ago. So just to show that you can go through and you can use SAR to extract features, and then you get this nice image on the right. You might see there's some little speckles all over the place. That's very easy to remove using something like classification aggregation or classification smoothing to clean all of that up. And two more examples. First one here is using UAV imagery. So just kind of a nice a variety of input data with originally starting with satellite, we have LiDAR, we have SAR, and now this is UAV, so very high resolution. So on the left is the source imagery. You'll see all the solar panels as kind of that dark blue. And over on the right, all of our detections are shown in red. So just to call out that this is actually a result and not just changing the colors. If you look in the detections, kind of in the middle on the left side, you'll see there's a couple of cars that have some red on them. So a few false positives from this model, but overall, the rate of actually classifying our solar panels is quite high. And so that's kind of one of the important things here. And this is a great example of where you could export this to polygons, or maybe you just want the centroid of each one, but you could get the area and coverage, things like that. And then the last little example to go through is for the car center detection. So when I was talking about the requirements for deep learning, which are an image and a region of interest, the little example shown on the region of interest page was using the ENVI feature counting tool to go through and mark the center locations of cars. And so this is a model generated with the center of those cars. So for this, you can use the solid distance as the width of the cars, and that's how you get these like little circle shapes at the center of the cars. Now, this is great if you just want to count them. If you actually wanted to extract the polygons and get something like the width or length of the features, then going through and using either a polyline with the solid distance or actually putting a little bounding box or polygon around each one of the cars would be a great way to extract that information. So those are all the little examples we have. So if you have any questions, feel free to use the chat box, questions box, and go to webinar. I have one more slide I'm going to show, and then we'll get to questions and discussion. So first thing to bring up, and this is more for people that are probably located on the East Coast or in the DC area. If you want to get your hands on this technology and learn how to use it and talk with some of the experts, we will be having a one-day class, which we're calling our Deep Learning Roadshow in Herndon, Virginia. One thing that's important to note about this, because of the facility that this training is located at, you have to be a U.S. citizen to attend. So, apologies if that's an inconvenience for some of you. That's just where our office is located at. But other information is listed on our website, and we'll also send out a link to this in the follow-up email with a video recording of the webinar as well. So with that, I'll turn things over to Megan for a few minutes here, and then we'll talk about questions.
Great. Thank you, Zach, for joining us today and doing this presentation. At this point, we will be addressing some of the questions that have come in. As a reminder, you can send us a question by using the questions chat box of your GoToWebinar dashboard. And first question is, when will this release be available?
Good one, and that's something I forgot to mention. This was available last Tuesday, so it's been out for just about a week.
All right, let's see. We've got a couple questions on, can you use ENVI and the deep learning module with hyperspectral data?
Great question. So the answer to that is yes, you could. This also brings up a very important concept and kind of difference between hyperspectral data and something like multispectral data. So if you have hyperspectral data with hundreds of bands, you probably have very small wavelength differences between the bands, and there's a lot of redundant information in there. And for deep learning, you typically want to boil it down to the most important information that represents your features. So if you were wanting to use hyperspectral data for deep learning, I would strongly suggest going through and doing some sort of data dimensionality reduction, whether that's a principal components analysis or independent components analysis or an MNF transform to reduce the number of bands to 8 or 10 or something like that. That's probably the best way to go. Because sometimes if you have too many bands, especially if they're all similar to one another, it can actually make your model not perform as well. So just keep that in mind. You'll probably want to do dimensionality reduction if you're going through that.
Good to know. Let's see. Here's a good question. Can you work with data above 8-bit?
Great question. So yes, you can. So you can work with any data type for ENVI Deep Learning. It will all be normalized and scaled to be from 0 to 255. So if you're worried about losing data or losing information, I wouldn't worry about it too much. For the example using LiDAR, we have the height of different features. And so for that, we have to scale our height to be something consistent. So that was actually 8-bit data. And for that, we just picked between 0 and 25 meters was our cutoff. And so that also helps make sure that it is consistent the next time it comes in, for every data set. So understanding that pre-processing step is very important. And with 8-bit or a pretty picture, you usually have enough information to go through and extract features.
All right. Zach, do you see a big difference between object-based image classification, such as feature extraction, and deep learning and machine learning?
Great question. So for some of the major differences, so if you're familiar with ENVI, there's the feature extraction module, and then there is the deep learning module. So similar concept of going through and extracting, pixels that you're interested in from imagery, but the main difference is that feature extraction uses an image segmentation based approach for going through and kind of clumping similar pixels together, versus deep learning, which is looking at your image, using that spatial context around features to go through and extract them. So they're similar, but they're different. I would tend to use something like deep learning, because deep learning behind the scenes, sometimes neural networks will start to pick up on textures and other things that you might be able to do with feature extraction. But my personal preference is deep learning. Plus, I like to use deep learning, so that's usually what I lean towards.
We're getting a couple questions, which I'm sort of going to mash together, so hopefully it'll make sense. But there's quite a few on how do you know how much you need to label to get a result, and how do you know if you will actually be able to get automatically extracted features with deep learning?
Okay, so good questions. So I'm going to flip-flop those. So first, I'm going to talk about what sort of features you can extract with deep learning, and then we'll talk about how much data you might need to extract those features. So if you want to extract something with deep learning from an image, the kind of rule of thumb is if you look at an image and if it takes you, a second or less to identify that as your feature, then chances are that you can extract that. Now, on that note, if you have to zoom in, zoom out, turn your head sideways to be able to know that that's the feature you're interested in, you're probably not going to be able to extract it with deep learning. So it's important to have that realistic expectation. The other thing is that if you want to try to extract your feature, you can always mark up just a couple of images to see if that it's something that you can extract. On to how much data that you need. The amount of data that you need really depends on your use case. If you just have a couple of images that you want to process and extract a feature for, you might just need to label one or two, especially if everything's very similar. The flip side is if you're wanting to create a production level deep learning workflow where you're extracting stuff from imagery, doing a little bit of classification cleanup, and converting that to vectors, you're probably going to want to have 20 or 30 at least. For the different models that I've worked on, I usually start to see really good performance right around 25 images, but that also depends on how rare your feature is. So if you have a feature you're extracting and maybe there's just 4 or 5 examples in each image that you have, then you're probably going to need 50 or 100 images because you typically need a couple hundred examples as well. So it's kind of a balance of how much data you have, how rare your feature is, and then also how complex your feature is. So if you have a feature that's complex with other things in your scene being confusing, you'll potentially need more data as well.
All right, you covered my very muddled question right there, so thanks for actually understanding what I was trying to say. Let's go to one that makes a lot more sense. Is it possible to train on an image that then refine the model by training on additional images iteratively?
Another good question, and yes, absolutely. So one of the things that's really nice about the deep learning module is that all of the tools for the task and the workflow for training, you can specify a deep learning model that has already been created. So the idea is that you could train on a data set, reuse a model that you have already created, and kind of continue training on your data. And so in addition to being able to continue training, you can also use it for a concept that's called transferred learning with air quotes around it, where if I train a model for extracting a feature and I want to extract a feature that maybe looks similar but is different, I could then I could try starting with a model that I've already generated, and I could use that information to maybe give my training a kickstart. So maybe it'll train faster and learn your feature faster.
All right, here's a question. Does ENVI Deep Learning work with the ENVI ArcGIS add-in?
Yes, and that's another good question. So just like almost all the tools in ENVI, if you're an ArcPro or an ArcMap user, we have a Python package called ENVI PyArc. There's also an installer that you can install, and if you get the latest version, which was just released to support the deep learning module, you can run these tools from an Esri environment. So I imagine that being more of using something like ENVI for generating your models, and then once you have that model generated, you could then classify imagery from that Esri environment. But since you're the end user, if that's what you want to do, you could also do everything from within Esri and not open up ENVI at all.
A follow-up to that one is there any way to send and use the ENVI Deep Learning in cloud computing instead of on a local machine?
Yes, so all of our analytics are also cloud compatible, or most of our analytics. So one thing that we even do sometimes when we're training neural networks is we will start up a machine on AWS or Azure and put ENVI and deep learning up there, taking advantage of more powerful GPUs.
Great. And I think we are going to do one last question, which is a pretty important one, which is where can I learn more about the deep learning tools in ENVI?
Great question. So there's documentation that comes with the tools. There's also some little examples in the docs that walk you through going through and extracting shipping containers. In addition to that, so I mentioned there's that deep learning roadshow that's going to be in Herndon. You can attend that, get some hands-on experience with the tools, and the content that we have for that class, one-day class, we can also share. So just some couple examples going through and doing the whole process, so you can get your hands on the tools and in a little bit more detail than the docs might provide for some things.
Thank you, Zach. With that, we are going to wrap things up. We appreciate everyone's attention on the line, and thank you again, Zach, for joining us today. If we didn't get to your question, then someone will follow up with you. And just a reminder that a recording of this webinar and the slides will be emailed to you in the next couple of days. It will also be available online at www.harrisgeospatial.com, and we encourage you to share it with your colleagues. Thank you, everyone, and have a great rest of the day.